In this video, we're going to do the free response 2007B number 5, and so it is a differential equation FRQ. And the reason I wanted to do this one is because this is an example where it's a differential equation, but you never end up solving it. Once we go through this, you're going to realize even here it talks about the particular solution and solve and what is y, but it doesn't actually ask you to find it, and we'll get there when we get there. But I just want to point out that just because I give you dy dx equals, that doesn't mean you're going to solve this and actually separate it, because actually this is not separable because it's plus y and you can't add or subtract. So just keep in mind they can give you a differential equation FRQ and you not ever solve it for the original. Okay, so the first thing says sketch a slope field. So since we just said we can't solve this for the original, we can't match the shape, so we're going to have to actually just plug in our points. Sketches, okay, I was making sure that I wasn't missing anything. So if you're sketching a slope field, I would make a table. You don't have to, but, and because my equation has x and y in it, I would put both. And so in this case, that means you're going to have to test every point. You can't just do x column or y row. You have to do every single point. So I'll start here when x is -1 and y is 2. That makes this 1/2 times -1 plus 2 minus 1. This is not required, so any work you can do in your head to save time, the better. I just am trying to make sure I don't lose anybody. So this would become -1/2 plus 1, which would be positive 1/2. So I want a positive slope of 1/2, which looks like maybe it'd be like that. Then I'm going to go to -1, 1. So this would be 1/2 times -1 plus 1 minus 1. So that becomes -1/2 plus 1 minus 1 is 0. So it's slope of -1/2. So negative needs to be going this way, and then try to make it a little less steep than -1. And then we have -1, 0, so that would be 1/2 times -1 plus 0 minus 1. So what is that? -1/2 minus 1 would be -3/2 or -1.5. So a negative slope, and it needs to be steeper than 1. So I'm going to make it like that. I just realized I'm doing my slopes wrong, aren't I? Wait, no I'm not. I'm going crazy. Okay, never mind. And so now we're going to start here. So when x is 0 and y is 2, well, we know if we multiply 1/2 by 0, that's just is going to go away, right? So I'm just going to go ahead and write it. 0 plus 2 minus 1 would be 1. So I want a slope of 1. Positive 1, which it should look steeper than your 1/2 a little bit. Then at 0, 1, that would be 0 plus 1 minus 1, so that's a slope of 0. So those slopes of zeros is going to be probably their own points, so make sure you get those right. So we draw a horizontal line. And then at 0, 0, that would be 0 plus 0 minus 1, so slope of -1. So something like that, which those look pretty similar. This should look steeper. Okay, now we go on to this column. So when x is 1 and y is 2, 1/2 times 1 is 1/2 plus 2 minus 1. So that's 1/2 plus 1, which would be 3/2. So it's positive and then steeper than 1. And then when x is 1 and y is 1, that'd be 1/2 plus 1 minus 1. So that'd be 1/2 and positive. So something like that maybe. And then lastly, I'm just going to do it down here, when my x is 1 and my y is 0. That would be 1/2 plus 0 minus 1, which would be 1/2 minus 1, which would be -1/2. which should look like this slope. So I know it's kind of hard to get your lines right, but if you showed all this work and you had your zero slopes and your positive and negative direction correct, you should be good to go. Okay, so for part B, it says find, that is the second derivative in terms of x and y. And then, so just focus on that first, and then we'll focus on describe the region and the xy plane in which all solution curves will be concave up. So, for part B, I'm going to go ahead and write down my first derivative. It just helps me to have it right here. So I'm starting with the first derivative. If I want the second derivative, I'm going to take the derivative of this equation. So, and this is like implicit because it's with respect to x. So when you do the derivative of 1/2 x, that becomes 1/2 plus the derivative of y is 1, but then you have to write times dy dx because it's not with respect to the same variable. And then the derivative of -1 is 0. So notice it says in terms of x and y. So what that means is once you take your second derivative, you normally have dy dx in there, and it wants you to replace dy dx with what it equals. So another way to write this would be 1/2. We don't really need 1 times, right? So just plus, and then in parentheses, we're going to replace dy dx with 1/2 x plus y minus 1, because that's what dy dx equals. And that is your second derivative. And so we could clean this up if we want to, right? I guess you don't really need the parentheses since it's plus. So we can just combine like terms, 1/2 minus 1. I'll go ahead and write 1/2 x plus y, and then 1/2 minus 1 would be minus 1/2. So that is your second derivative. So even if you don't understand the second part of this question, at least you got that down. And now it says describe the region in the plane when all solutions, which solution curves are the original, when the original function is concave up. So how do we know when it's concave up? When the second derivative is positive. So I'm going to write this out. Y is, because y is the original, concave up when the second derivative is positive. So what's another way to write positive? When the second derivative is greater than 0. So what we're going to do is we're going to take our second derivative equation and set it greater than 0. And now just to get the, how does it word it? The region where it's concave up, I'm just going to solve this for y. So I'm going to keep my y positive, I'm going to move over my x and my constant to the other side. So I'm going to do plus 1/2. So then you have 1/2 x plus y is greater than 1/2, and then minus 1/2 x. So that would be when y is greater than 1/2 minus 1/2 x, or you could switch that to be negative 1/2 x plus 1/2. When this is true for any ordered pair where the y value is greater than 1/2 minus 1/2 times the x value, the function is concave up. So I know we haven't done anything like that before, but it's using a fact we know. And again, if you could do this part, you'll get the majority of your points just getting the second derivative. Okay, so for part C, it says, let's go back, let y equals f of x be a particular solution to the differential function with an initial condition. Okay, so they give you an IC. Does f have a relative minimum, maximum, or neither at 0? So if you think about this question, how do you know a relative min, max, or neither. That's talking about your critical points when the first derivative is 0 or undefined. And then we have a way that if you determine it's a critical point, because you can't really do a sign chart in this case, it's going to, I'm trying to think why. If you worked it out, you're going to get stuck. I'd have to actually work it out to remember why. But we have another fact, it's the second derivative test, that since we now have the second derivative also, the concavity will tell us if it's a critical point and it's, here, I'm going to go and write this down. The second derivative test, you don't have to write this down on your free response, but states that if, I'll say x equals c is a critical point. So what does that mean? A critical point means y prime equals 0 or undefined. Then if it's concave up, so think about concave up, then that's a minimum. X equals c is a min. And if it's concave down, I'm going to put c down, think about concave down, looks like a frown, then that creates a maximum, so x equals c has to be a maximum. And then if for some reason your second derivative is undefined, or it's neither, then that would be when it's neither, but that's probably not going to happen. So when we have two things to prove, to know, is this at x equals 0, which notice they give you the points at x equals 0, that's our initial condition. So we have our x and y. At this point, if it's a critical point, and if we can determine the concavity, then we know is it going to be a min or a max. So the first thing we're going to do is check if it's a critical point. Everything, all these words I'm writing you don't really need. Check if critical point. So what you need to write down, I'll put in blue, or I'll put in green. Now what point am I talking about? I'm talking about at x equals 0, we're trying to determine is it a relative min-max or neither, and we know at x equals 0, the ordered pair is 0, 1. So we're going to plug this into our derivative first. So the notation you use is the derivative, and you draw a line and you write that ordered pair. That, what is this like saying f of 0? It's saying the derivative at this point equals 1/2 times x, which we said is 0, plus y, which we said is 1, minus 1. So we can see that 1 minus 1 is 0, and that becomes 0, so this whole thing is 0. So we checked it, and the derivative is 0, so we know it's a critical point. Now we're going to check the second derivative. So now we're going to check second derivative for concavity. So we're going to take our second derivative and plug in that same point. So this is our second derivative in terms of x and y. So 1/2 times 0 plus 1 minus 1/2. So what is that? That's 0 plus 1 minus 1/2, which would be a positive 1/2. So because the second derivative is positive, we know our function's concave up. So I'm going to say because d2y dx2, the second derivative is positive at 0, 1, function is concave up. So if you notice, we're not done, right? But now we can actually answer the question. So by that second derivative test, we know it's a critical value, and we know it's concave up, so that means if you create concave up, that creates a minimum. So x equals c is a minimum. So this point is a minimum. So we just got to put that in words real quick. I'm going to say part C, continued. Oops, I put C, but not the C for continued. So you would write out because at, you can put that point 0, 1, dy dx equals 0, and the second derivative is positive, comma, 0, 1 is a relative, what do we say, if it's concave up, it creates a minimum, relative minimum. So I know we haven't done a lot using that second derivative test, so let me know if you need more help with that. If this notation confused you, you could also write it like this. Just be careful, because the derivative doesn't always equal 0. At this point it equals 0, so that's why it's good to use this notation as you're doing your math. Okay, so for part D, honestly, if you are striving to just pass, I would not worry about part D. To me, this is more like an extra credit type question. It is not a lot of points on your test. You could still get a 5 and not understand this, but I am going to work it out for those of you that want to see it, but I don't want to stress those of you out that are already stressed, okay? This is only for people that need a little bit of a challenge maybe, or you just are curious. So for part D, it says find the values of the constant m and b for which y equals mx plus b is a solution. So we did at the beginning of chapter 6, we didn't spend a lot of time, but we talked about solutions, two differential equations, and verifying solutions. So what we did is, so we're trying to determine is y equals mx plus b. So we're going to plug this in, and we plug mx plus b in for y, and we plug its derivative in for dy dx. So what is the derivative dy dx equal to for this equation? Well, we know m is a constant, or a coefficient, right? So the derivative of mx is just m, and the derivative of b goes away. So we have what y equals, and we have what dy dx equals. So what we're going to do is we take our differential equation, and rewrite it, and I plug in my differential equation, or what my dy dx equals and what my y equals. So I'm kind of getting it all in terms of x. So dy dx equals m, and then I keep my 1/2 x plus, and then I'm going to plug in my y, which is mx plus b, and then you have your minus 1. Okay, so this is the part that gets kind of confusing to solve for this. So this is the best way I've found to solve for it. There are probably different ways you go about thinking about this, but we're trying to figure out what do m and b need to be for this statement to be true. So what I would do is first, do I really need these parentheses? No, because it's just plus. So I would drop those parentheses and kind of see what you got better. And then what I see here is that these both have x, right? So you could factor out an x of just these first two terms. So that becomes m equals x times 1/2 plus m, and then you have plus b minus 1. So if we think about, keep in mind m and b are numbers, correct? So for this side to equal this side, you could even think about adding over here a 0x. The only way these two sides are going to equal, because we don't have an x over here, is if this whole x term disappears. Right? These two sides can't equal until this x term is gone, because x doesn't always equal a number in this case. Remember, we talked about when we solved these, if you got x equals a number, then it's not a solution. You want the two sides to be identical. So for this two sides to be identical, this coefficient for x, 1/2 plus m, needs to equal 0. And then this plus, this b minus 1 is like the m, right? It's like 0 times x plus this last stuff is like the m. So this b minus 1 needs to equal m. And just think about these first two terms equaling, and then this b minus 1, treat that as like one term, and those constants equaling. So now we can solve this for m pretty easy. Minus a half minus a half. So m equals negative a half. So then we can plug in m over here. I'll leave room to work, but show I'm plugging this m in over. So you had to do this one first. And now we know b minus 1 needs to equal negative a half. So b needs to equal negative a half plus 1, which would be positive 1/2. So those would be the constants m and b for this solution to work out. And again, don't stress too much about that, but I mean, obviously anything could come up on your AP test, but that's not going to be a major topic or anything. But these slope fields, taking second derivative, even the second derivative test, I would ask questions if you didn't quite understand that. Let me know if you need help with anything else.